Hey guys, so we are starting Cambridge International AS and A levels chemistry coursebook, and in this video we are going to cover self-assessment questions of chapter 6 Enthalpy Changes. Question number 1. Classify each process as exothermic or endothermic process. Part A, burning of magnesium in air. Burning reactions are actually combustion reactions, combustion or burning with oxygen. So combustion processes are always exothermic process. So first reaction will be exothermic reaction. Part 2 is crystallization of copper 2 sulfate from a saturated solution. In this process, we are going to start from the saturated solution and we are going to change into crystals, the solid state. So liquid is changing into the solid state. So what happens actually during the crystallization process, particles of the liquid substance will come closer and they will form highly ordered structure. So it means in case of the liquid, they will be having more kinetic energy and more movement. And in case of the crystals, now they will be having less kinetic energy. So energy is going to release out from the system. So this process will be exothermic process here. C. Thermal decomposition of magnesium nitrate. Therm means heat and decomposition means breakdown. So breakdown of magnesium nitrate by providing heat. So this process will be known as endothermic reaction. So remember, thermal decomposition processes are always endothermic. D. Fermentation of glucose by yeast. So, what happens in this process? In this process, actually, fermentation is the breakdown of the glucose by the help of yeast enzyme. So, whenever we have glucose, in case of the fermentation process, or maybe we have the carbohydrate breakdown in case of respiration process in plants and animals, these processes are always exothermic. Why? Because whenever we have glucose or carbohydrate, we break down the glucose or carbohydrate and it produces energy at the end. So these processes will be known as exothermic process. So evaporation of seawater. In this process, seawater is actually going to change into vapors, into the gas state. So water is changing into gas state. In case of the water liquid, it was having a little less kinetic energy, but when it is going to change into vapors or gas state, it is going to increase in kinetic energy. So kinetic energy is needed here. So energy, water will absorb energy so that it can change into vapors having more kinetic energy now. So this process is absorbing energy or heat. So this will be known as endothermic process. So here are the solutions for the question number 1. Moving towards question number 2, draw full reaction pathway diagram including activation energy for the combustion of sulfur to form sulfur dioxide. So our reactant will be sulfur, and when we are doing the combustion, it means we are going to react it with oxygen O2. So oxygen and sulfur is going to react together and producing sulfur dioxide at the end. Question number 2. Draw full reaction pathway diagram including activation energy for the combustion of sulfur to form sulfur dioxide. In this reaction, combustion of sulfur is our reactant side and it is going to form sulfur dioxide at the end. So, sulfur combustion means sulfur is going to react with oxygen. In combustion, it has the oxygen as the other reactant. So, these two are going to react and producing sulfur dioxide at the end as the product. And as we discussed already, combustion reactions are always exothermic reaction. So, here we are going to produce the energy pathway diagram for the exothermic reaction. So whenever we make the energy pathway diagram or the reaction pathway diagram, we take energy on the y-axis and we are going to take the reaction progress on the x-axis. So at the top, we make the all the reactants here. Okay, our reactants will come here because now this is the exothermic reaction. So products will be little down here. Products will be having less energy now. And for the activation energy, we always make a hump here, starting from the reactant towards the product. So if we have a complete look for this type of the reaction pathway diagram, here will be the diagram. So we have the reactants at the top here, sulfur in the form of solid, its original state, plus oxygen in the form of gas. They are going to have the combustion reaction and producing a product SO2, and SO2 is a gas. Okay, so activation energy hump we are going to have here. So here two things are very important: how we can make the activation energy and enthalpy change lines here. Their lines or arrows are very important here. For the activation energy arrow always start from the reactant and goes toward the top. So EA here is the activation energy, and this arrow is starting from the reactant and going towards the top of the graph. Okay, that will be the line and direction for the activation energy. And for making the enthalpy change or the delta HF here, the arrow will start from the reactants and always goes towards the product. So from reactant towards the product, it will be the direction and total length as well. Reactant towards product. So that will be the delta HF graph. And this whole diagram is for the exothermic reaction because combustion reactions are always exothermic reaction. Then we have the second reaction part B here, and it is saying it is an endothermic reaction and it is having H2O gas plus carbon in the form of solid reacting and making hydrogen gas plus CO gas. So H2O and carbon is our reactants, hydrogen and CO is our products here. So now this is an endothermic reaction. It means the product will be having more energy as compared to the reactants. So products will be little up as compared to the reactants. So here will be our graph for the endothermic reaction. So here are the reactants little down because it is an endothermic, so reactants will have less energy. After absorbing the energy in endothermic reaction, products will be having more energy and it will go towards the top. So again, the arrows are very important to make here. Activation energy arrow will start from the reactant and goes till the top. So this will be the EA activation energy graph. And for the enthalpy change, it always start arrow always start from the reactant till products. So now the arrow is upward in case of endothermic reaction, and it is also even smaller than activation energy because it is from reactant to products only. So that's all about the question number 2. Question number 3: identify each of the following reaction as delta HR, delta HF, and delta HC. So here delta HR is the delta H reaction, and this symbol you can see at the top, circle with a small line inside. This symbol means this reaction is taken under standard conditions. And standard conditions, we have pressure 101 kilopascal, temperature should always be 298 Kelvin, and third standard condition is that the reaction should be done under normal physical states such as solid, liquid, and gas. So this symbol is telling you about all the standard conditions. So delta HR is the delta H reaction here. Delta HF means it is the delta H enthalpy change of formation here. Delta HC means it is the enthalpy change of combustion here. So before you identify these reactions, you have to learn about the definitions of these three terms. Then it will be really easy for you guys to understand these types of reactions. So, moving towards the definition, standard enthalpy change of reaction means enthalpy change when reactants shown in the stoichiometric equation means a balanced chemical equation. So whatever the number of moles of reactants are given in the balanced equation, when they react and give product, but under standard conditions. Why? Because we have the symbol of standard condition here. So in simple, when we have reactants and they change into products, same like the balanced chemical equation, they should have the same number of moles. In that case, the enthalpy change will be known as enthalpy change of reaction. Okay, then enthalpy change of formation. Enthalpy change of formation means when one mole of compound is formed, when the product should be just one mole of the product is going to form from elements under standard condition. This thing is very important that for the formation, starting reactant should always be elements. Elements will react and make one mole of product at the end. In that case, the enthalpy change will be enthalpy change of formation. Remember one more thing here. In case of the enthalpy change of reaction, you cannot take elements. Here there will be just reactant and products but not the elements. We are not taking the elements in case of the reaction. But in case of the formation, we are taking elements and we are making one mole of product only. So we are going to see these reactions and we can easily identify after these definitions. Then the last one is enthalpy change of combustion. Change of the combustion is when one mole of the substance is burnt. We are going to burn one mole of any substance with excess oxygen. Oxygen can be any number of mole. So in that case, the enthalpy change will be known as enthalpy change of combustion. So now we can go back to our reaction and we can identify all one by one. Okay. So very first one, A. MgCO3 is going to produce MgO plus carbon dioxide at the end. So this reaction we can see one by one. Is it delta HR? Is it delta HF? Or is it delta HC? Okay, for the combustion, there should be oxygen on the reactant side. So we don't have oxygen in this first case. It means it is not delta HC. And for the formation, we need elements in the standard state as the reactants. We have MgCO3. MgCO3 is not an element, it is a compound of magnesium, carbon, and oxygen. We have three different elements here joined together and making one compound. It is not separate elements. So, first is not delta HF, but it will be delta H reaction. Delta H reaction was saying that products can be made from the reactants just in balanced chemical equation, but they should not be elements. So yes, it is delta H reaction because here we have the products and reactants. We don't have any oxygen in the reactant side and we don't have the elements. So first one will be just delta HR. And don't forget to write this standard symbol on it. Part B, carbon in the form of graphite with oxygen in the form of gas is producing CO2 as a gas. So we are writing carbon in the form of graphite because carbon has different allotropes. Allotropes means different forms of same element. Carbon can exist in the form of diamond, it can be exist in the form of graphite, so it have different allotropes. So graphite allotrope we are using here. So it is an element. Oxygen is also one element. Okay, it is not a mixture or compound of anything, it is just an element here. So two elements we have and producing one product. So if we go back to the definitions, you can see here for the formation, it was saying elements and it should produce one mole of the product at the end. So yes, we have elements and it is producing one mole of product. Number written at the start is actually number of moles. So here it is 1. So it means it is the delta HF. This will be the delta HF. Plus It will also be delta H combustion because we have oxygen on the reactant side. So it is also delta H combustion. So we will write it as delta H formation and delta H combustion. It will not be delta H reaction because delta H reaction don't include elements. Delta H reaction will have only the compounds. So it will be just delta H formation and combustion here. Then next C. We have HCl in the gas form plus NH3 in gas form. It is producing NH4Cl as solid. So see one by one, it is not the combustion because we don't have oxygen. It is not delta H formation because we don't have elements in the standard state. It is delta H reaction because we have compounds here, we don't have elements. So it will be delta HR only. If we see the next one, D, here you can easily identify we have the hydrogen element, just one element. We have 1 by 2 oxygen, again element, and it is producing 1 mole of product. So yes, it is delta HF. It is delta H formation. And it also includes the oxygen here, so it is also delta H combustion. But it is not delta HR because it has the elements on the reactant side. So it will be just delta H formation and delta H combustion. Here are all the solutions for the question number 3. So when we are talking about the B and D, it is the delta H formation of carbon dioxide. Formation is for the carbon dioxide, 1 mole of the carbon dioxide is going to produce here, and combustion or the burning is happening for the graphite. So we can write it as that it is the delta H combustion for the graphite. Same for the part D, we can say that it is the formation of the water H2O and it is the combustion of the hydrogen H2 on the reactant side because formation is the product side and combustion will be the reactant side. So that's how we can write all these parts. Question number 4. Calculate the energy transferred when temperature of 75 cm cube of water rises from 23 degrees Celsius to 54 degrees Celsius. So we have the formula for the energy transfer that we can use here. So that is Q is equal to mc delta T. So in this Q is equal to mc delta T, m is the mass of the liquid, C is the specific heat capacity, T is the delta T is the temperature change. So this formula we most of the time use for the water. So it is actually the mass of the liquid is the mass of the water. We need the mass of the water in grams. Specific heat capacity of the water is also a fixed number. And we need the temperature change, how much temperature has been changed after some time. So in place of the m, we have to write the mass of the water. Right now, in the part A, volume of the water is given as 75 cm cube. So for this formula, we have some assumptions that are also true that 1 cm cube of the water is actually equal to 1 gram in weight. So it means if we have 75 cm cube of the water, it will be equal to 75 grams. So in place of the mass, we can write 75 grams. Specific heat capacity of the water is a fixed constant number. So it is 4.18 joule per gram per degree Celsius. And delta T we can find by just subtracting the final temperature minus the initial. So 54 minus 23 will give us the number 31. So in place of the delta T, we can write 31. So when you just solve it, you will be getting the answer 9718.5. So we most of the time write the answer in three significant figures. So it will be 9720 joules. Part B, when 8 gram of the sodium chloride is dissolved in 40 cm cube of the water, the temperature falls from 22 to 20.5 degrees Celsius. Now calculate the energy absorbed by the solution when sodium chloride dissolves. So here again we can use the same heat transfer formula that will be equal to Q is equal to mc delta T. Remember one thing here for this part B, that enthalpy changes we always use just for the liquids. And there is a reason behind it. Why don't we include the mass of sodium chloride 8 gram here? Because when we are heating the water, water is going to absorb or release the heat. Water will be responsible for the temperature change here, not the sodium chloride. So enthalpy change or the temperature change will be done just by the water, just by the liquid. So only the liquid mass will be included here, not any solid mass. So we are going to write 40 cm cube equal to 40 gram in the formula. So in place of the mass, we are going to write just the water mass, not the sodium chloride. And C will be the specific heat capacity for the water just. And delta T temperature change will be 22 minus 20.5 will give us the number 1.5. So we can just solve it and we will be getting the answer 250.5 joules, and in three significant figures it will be equal to 251 joules. Part C. A student added 50 cm cube of the sodium hydroxide solution. It is liquid state. And it is adding 50 cm cube of hydrochloric acid in it. Both solutions were at 18 degrees Celsius at the start. When the solutions were mixed, a reaction will happen and the temperature will rise to 33 degrees Celsius. How much energy is released in this reaction? Again, the same Q is equal to mc delta T formula we can use, but here we need some assumptions before solving the question. So let's move toward the solution. So we have two solutions here. We have 50 cm cube of the sodium hydroxide and we have 50 cm cube of the hydrochloric acid. So total mass of the solution we can just find from the total of the 50 plus 50 of acid and alkali. So it should be 100 cm cube volume that will be equal to 100 gram in mass. So what we are assuming here, we are saying that 50 cm cube of the acid plus the 50 cm cube of the alkali will having the same mass just like the water. Okay, we are going to take them as the solution. And 100 cm cube we are taking equal to 100 gram just like the water. So here the specific heat change or the total heat change will be done by the help of these solutions. So we are taking the mass of these solutions here. So specific heat capacity we are going to take same as like water, and we are assuming that the heat capacity of this solution is same as heat capacity of water. So these are the two assumptions that are needed here before solving this question. Now we can just apply the same formula. Q is equal to mc delta T. In place of the m, all the liquid mass plus specific heat capacity of the liquid, which we are assuming is same like the water. So it should be equal to 4.18, and the temperature change multiply by temperature change. So we have 33 degrees Celsius and 18. So we will just subtract it and at the end temperature change will be 15. 33 minus 18 will be 15. So we can plug in all the values, solve it, and you will be getting the answer 6270 joules in three significant figures. Question number 5. Explain why enthalpy change of neutralization of 1 mole of sulfuric acid is not the standard enthalpy change of neutralization in kilojoule per mole. So in this question it is saying why the sulfuric acid neutralization will not be standard. So, to see if it is standard or no, we have to first see the definition of the neutralization. So, if we see the definition, enthalpy change of the neutralization in standard condition says that it is the enthalpy change when 1 mole of water is going to form by the reaction of an acid with alkali. So, in neutralization is the reaction of alkali and acid. two are reacting but producing just 1 mole of water at the end. If they are producing 1 mole of the water, then it will be standard enthalpy change of neutralization. If it will be different than 1, maybe less or more, in that case it will not be standard enthalpy change of neutralization. Now we have to write equation, neutralization equation for the sulfuric acid with any alkali. So let's say we have the sulfuric acid reaction with sodium hydroxide. If we write a balanced chemical equation, we will be having H2SO4 plus 2NaOH is producing Na2SO4 plus 2H2O. So here you are getting two water molecules, 2 moles of water. We need 1 mole of water to say it's standard. It will be standard only if we have 1 mole of water here. So it means the sulfuric acid produces 2 moles of water at the end. So that is the reason it will not be standard. It will be twice than the standard. So this reason you can write here that 1 mole of the sulfuric acid react with 2 moles of sodium hydroxide and producing 2 moles of water at the end. So by definition, it is not the standard enthalpy change of neutralization because standard will need just 1 mole of water at the end. So it is twice as the enthalpy change for sulfuric acid. Question number 6. A student added 10 gram of 0.25 mole of sodium hydroxide to 40 cm cube of water to make a concentrated solution. All the sodium hydroxide will just dissolve in it. Student is going to check how much temperature is going to rise. And student suggested that if I am going to perform this reaction, this is going to give me an accurate value for the standard enthalpy change of solution at the end. But this is not a right information here. This method is not a right method. So we have to suggest two reasons why the student is incorrect here. So see, in this case, the student is just going to see that the sodium hydroxide and water are going to just dissolve in each other, and it is going to see just the temperature change. But these are not just two factors which are going to be responsible for the enthalpy change of solution. So student is, what we can write here, that student is just checking the reactants are going to dissolve, and it is just checking the temperature rise here. So these are not just the factors which are responsible for enthalpy change of solution. There can be some other factors. Because of this, the value of enthalpy change of solution can be different. So this method is incorrect. So which other factors can change the value? That can be time. How much time it is going to take to dissolve the sodium, and how much energy loss can be there. Energy loss can happen to the thermometer, it can happen to air, it can happen to even calorimeter. So how much energy loss is going to happen, that is going to change the enthalpy change of solution value. And student is also assuming that the specific heat capacity of this solution is also equal to water. So it can be even a wrong assumption. So this can change the value of solution enthalpy. Question number 7. Student calculated the standard enthalpy change of combustion of ethanol by calorimetry, and it is getting the answer minus 870 kilojoule per mole. But if we see the data booklet, this value is completely different. It is minus 1367, that is the actual answer. Explain why there is a difference between these values. So, exact actual value can be different from the experimental value again due to multiple factors. It can be heat loss, it can be any other factor because of which these values can be different. So, what we can write here, we can say that this experimental value is different from the actual value because we can have the heat loss during the experiment. Heat can be lost to the surrounding from the flame, or it can be lost by the help of calorimeter, It can go to the thermometer or air. So it can be any reason of the heat loss here. It can also be the incomplete combustion of ethanol. So, incomplete combustion of ethanol will not give us the exact enthalpy change of combustion at the end. It can also be the mass loss, maybe some of the ethanol is going to evaporate. So, it means mass or the weight of the ethanol is going to be lost here. So, overall value will reduce. So, these can be the reasons that the student is getting a completely different answer from the standard value. Question number 8. Draw an enthalpy cycle to calculate delta HR for the reaction. And in the reaction, we have 2 moles of aluminium plus Fe2O3 is giving us 2Fe plus Al2O3. So we have to make an enthalpy cycle for delta H reaction. So, making the enthalpy cycle for delta H reaction, we have a general cycle that we can follow here. So, all the reactants we are going to write here and at the top, and it is going to move towards the product. So, product from the balanced chemical equation we are going to write here. And changing the reactants into the products will be the delta HR, delta H reaction. So elements we are going to write here at the end. So changing elements should be in their standard state. Changing the elements directly into the products will be a direct method having the delta H2 as the value, and changing the element into first of all reactant will be delta H1, and then this reactant will move toward the product. So elements towards reactant and then the product, this will be an indirect route. So this will be a two-step method. It is a one route, but it has two steps. So two steps indirect route. You will always have a red dotted line here so that you can identify which side is the indirect route here. So delta H21 is the direct route, one step, and this is the indirect route having two steps here. So using the same, we can just make our own cycle for this particular reaction. So we have 2Al in the solid plus Fe2O3 in the solid as the reactant. We are going to write them here. And we have 2Fe solid and 2Al2O3 solid as the product we are going to write here. And we will be having delta H reaction in between them. And now we have to write the elements in their standard state. So you can check any side, maybe reactant side, maybe product side, and you can just write the elements. Let's say we are going to check the reactant side now. So in the reactant side, see which things we are using. We are using first of all 2 aluminium. Aluminium exists in the form of Al monatomic atom, and it will be in the form of solid, that is the standard state of the aluminium. So 2 aluminium in the form of solid state they exist. Now we are using Fe2 in the reactant side, means 2Fe. Why can't we write Fe2 here? Because Fe don't exist in the form of diatomic element. It exists in the form of monoatomic Fe. So we have to write 2 times Fe again in form of solid state. So solid state we are going to write here. Plus we have total 3 atoms of oxygen here. Oxygen exists as diatomic molecule. Oxygen exists as O2. So we have to write oxygen in the form of O2. Now we need total 3 atoms of the oxygen. It means you need one complete oxygen plus you need half oxygen so that it can total be equal to 3 atoms of oxygen. Okay, so complete O2 plus 1 by 2 O2 we need. So complete O2 is 1 plus half. So we are going to write it 1 and half O2 that we need here. So 1 and half O2 is needed here in the form of elements. So that's how we can just make the cycle, and here is the final cycle that we have. Reactants here, and we have the delta H reaction. We have the products over here. We have all the elements in their standard state here. This will be the delta H2, this side is the delta H1, and moving from the delta H1 towards this will be an indirect route having the red dotted line here. Part B is saying calculate the delta HR using the following information. So for this reason, first of all, we have to identify where we have the delta H formation of Fe2O3 and where at which side we have the delta H formation of Al2O3. So if you see in the reactant we have Fe2O3. It means the elements are combining and making Fe2O3. So it means this delta H1 here is actually delta H formation of Fe2O3. Elements are making Fe2O3. So this value of delta HF formation of Fe2O3 we can write in place of delta H1. On the product side, we have Al2O3 as the product. So elements are changing and making Al2O3. So here delta H2 is actually equal to delta H formation of Al2O3. So we can write Al2O3 formation value in place of delta H2 and we can calculate the final delta HR. So, from the chapter, we have the formula that the enthalpy change of direct route is equal to enthalpy change of sum of indirect route values. So on the indirect route, we have delta HR and delta H1. So their sum should be equal to delta H2. So our formula will be delta HR plus delta H1 is equal to delta H2. We need just delta HR. So delta H1 will go on other side and subtract. So in place of the delta H2, we have to write the value of Al2O3 that is minus 1675.7. We are going to write it here. And in place of the delta H1, we have to write the value of Fe2O3 that is minus 824.2. We can write it here. This negative and the negative of the formula is going to make this value positive, and then you are going to just solve it and you will be getting the final answer minus 851.5 as the delta HR for this particular reaction. Question number 9. Draw an enthalpy cycle to calculate the enthalpy change of formation of ethanol using enthalpy change of combustion. So we have to make a cycle in which we are going to write enthalpy change of formation of ethanol and we are using combustion values. So formation and combustion, when we relate in one cycle, we have a method to make this cycle. So here is a general form of this cycle that we can have. So in this case, we are going to write all the elements on this left side plus oxygen because it is going to involve the combustion. These elements are going to form the product here. Compound formed we are going to write here plus the same number of oxygen we again going to write here because this formation is including combustion as well. So this is a method to make this cycle. And then elements directly can go into the combustion product. Here at the end, we will be writing combustion product. And combustion products are carbon dioxide and water. In this case, in ethanol case. So we will be writing them. So here we will be writing combustion product. Elements can change into combustion product directly. It will be delta H1. So elements are changing into compound and then this compound can change into combustion product. So this will be delta H2 and this side is an indirect route. You can see this red dotted line. So same way we can just write or we can just make this cycle for ethanol now. So in place of the compound formed, we are going to write ethanol because ethanol formation we need here. And in case of the elements, we are going to write all the elements which are present in ethanol. So in ethanol, we have carbon, hydrogen, oxygen, three different elements. And we are going to have a balanced equation at the end. And at the end, here we are going to write the combustion product. So here is the final cycle. First of all, we can write just the elements and we can write the compounds formed. So compound formed is the ethanol, and we have oxygen with it. Later we can balance this equation as well. And on the reactant side, on the element side, we are going to write, because in ethanol we have two carbons. So 2C we are going to write, and carbon in the form of graphite we are using. Carbon don't exist in the form of C2. It exists in the monatomic form. So 2C we are going to write, because elements should always be written in their standard state. And in ethanol, we have total 6 hydrogens, 5 plus 1. So 6 hydrogen. Hydrogen exists in the form of H2. So we can write 3H2 total, that is going to make total 6 hydrogens. And then we can write the oxygen and also balance it. So we have 3 complete, 1.5 means total 7 oxygen here. 3 complete O2 means 6 oxygen. Half means the 7th oxygen. And on the other side, we have 3 complete, 6 oxygen here, and 1 oxygen, 7 oxygen here. So both side we have the 7 7 oxygen balanced equation now. And now we can write the combustion product as well. So this is going to make carbon dioxide and water. So you have to balance it as well. How much carbon we have here? 2. So it means in this case we will be having 2 CO2, and then we will be having 3 H2O. So all the carbon, hydrogen and oxygen numbers should be balanced. You can see this side and you can balance the combustion product, or you can also see this side and you can balance the combustion product. So both sides you can use. And then you can also write here that which thing are going to form here. So here we have the formation of the ethanol. So this delta HF will be the formation value of ethanol. And which combustion is going to happen? On this elemental side, 2 carbon in the form of graphite have the combustion. So it will be the delta H combustion 2 times, because 2 graphite are going to have the combustion here. And we also have the hydrogen combustion here. 3 total hydrogen we have. So 3 time combustion value of the hydrogen. So this whole will be equal to delta H1. On other side, we have the ethanol combustion, and we have just 1 mole of the ethanol. So just one time the combustion value of the ethanol we can write, and it will be equal to delta H2. So these values later we can use to find the formation value. Part B is saying that find the delta H formation of the ethanol by using the combustion of graphite, combustion of hydrogen, and combustion of ethanol values. So delta HF plus delta H2 will be equal to delta H1, because HF and H2 is on the indirect route. It is equal to delta H1. So if we want to find the delta H formation, delta H2 will go on other side and subtract. So here I'm using the different colors so that you can just easily find and identify the values. So in place of the delta H1, we are writing 2 times the value of the graphite and 3 times the value of hydrogen. So here is the 2 times value of graphite, 3 times value of hydrogen, minus of the formula, and delta H2 value. Delta H2 right now is the combustion of ethanol. So combustion of ethanol minus 1367.3 we can write here. So minus of this and minus of formula will make it positive. Later you can just solve it and you will be getting the final answer minus 277.1 as the delta H formation of ethanol. Question number 10. Look at this equation. Which of the following gives the correct value for the enthalpy change of this reaction? So we have to see the delta HR, that which reaction from this ABCD is the correct equation we have. Which one is the correct relation here? So before finding the correct relation, we have to make enthalpy change of reaction cycle for this one. And then we can just find the correct relation here. So if we just try to make the delta H reaction, so here will be the cycle. We will be having all the reactants here. we will be having all the products of the balanced chemical equation here. So reactants to products is the delta H reaction, and we are writing the elements in their standard state here. So we have 3 Mg. So 3 Mg exists as Mg monatomic in the form of solid state. We have F2 means 2Fe total in the form of solid state. We need O3 means 3 oxygen atoms. So one complete oxygen and half oxygen is giving us O3. So that's how we can just write the elements, and oxygen will be in the gas state because elements should always be in their standard state. Okay, then we can write the delta H1 here is actually the formation of Fe2O3, and we have just one Fe2O3. And on this side, the delta HF we have for the formation of MgO. MgO product is going to form from the elements. So we have 3 times the formation value of MgO. So we can write our relation of delta HR. It will be equal to delta H2 minus delta H1. So in place of the delta H2, we are writing 3 times formation of MgO minus, in place of the delta H1, we are writing 1 time the formation of Fe2O3. So if you just compare it, this will be our relation D. So D will be a correct relation here for this type of the equation, in which we have the delta H reaction equal to 3 times the formation of MgO minus the delta H formation 1 time for the Fe2O3. Question number 11. Use the information in the figure and the information below to demonstrate that the average bond energy of the CH bond is 415.9 kilojoule per mole, and the delta H formation of methane is given, delta H atomization of 1 by 2 hydrogen is given, and delta H atomization of graphite is given as well. So here is the figure 6.13, in which we have an enthalpy cycle, and this cycle is actually used to find the bond energy of single CH bond. In this cycle, you can see here we have the CH4, and by delta H, it is going to change into elements carbon and hydrogen. But these are not the standard elements right now because hydrogen don't exist as hydrogen, it exists as H2. So this is just the CH4 bonds are going to break here. So it is changing into separate carbon and hydrogens. And here you have the carbon graphite and 2H2 gas. These are the elements in their standard state. So when elements in their standard state change into a product, this is known as delta HF. So we have the delta H formation of methane here. And when elements change into direct simple atoms only, which are not the standard states, these are just the simple atoms in the gas state. In that case, we use the delta H atomization AT. So delta H atomization means changing the elements into atoms in the gas state. So we are using delta H atomization here. We have one carbon, so it means we are going to use the graphite or carbon value 1 time. And we have total 2H2 means 4 hydrogens are going to make at the end in the gas state. So it means atomization of 4 hydrogen atoms are going to happen. So 4 times atomization value we are going to use here. So this is the direct route here, and changing the elements first into the product and then into the atoms is the indirect route here. So we have to use this cycle and we have to use this information given to see that CH bond energy is actually 415.9. So before finding the CH bond energy, we first of all need this delta H value. It is not given in this information. Only then we can find the CH bond. So to find the delta H, we can use our formula that the enthalpy change of direct route is equal to enthalpy change of indirect route. So we will be having right now the delta H plus delta H formation of CH4. This one will be equal to direct route means atomization of the graphite and 4 times atomization of hydrogen. This one. We need the delta H just, so delta H formation of CH4 will go on other side and subtract. Now just put all the values. Delta H atomization graphite 1 time we have the value, and 4 times the delta H atomization of hydrogen, 4 times 218, minus of the formula, and then delta H formation of CH4 is also negative, so minus and minus will make it positive. Solve it, and at the end you will be getting the delta H value, that is 1663.5 kilojoule per mole. This delta H is actually when complete CH4 is going to break into 1 carbon and 4 hydrogen. So we have to first of all see that in CH4, how many CH bonds we have that are taking this delta H energy to break. So we need the CH formula, the open structure of the CH4. So CH4, in which we have 1 carbon attached with 4 hydrogens. If you see here, this site have one CH bond, this is second CH bond, this is third CH bond, this is fourth CH bond. So in one CH4 we have 4 CH bonds. So 4 CH bonds are going to have delta H 1663.5. So for the one CH bond we need to just divide this value. So dividing this value with 4 will give you the answer 415.9 kilojoule per mole. And this is a positive answer because bond breaking is endothermic reaction. So 415.9, the exact answer we are getting. This energy will be needed to break one CH bond in methane. Question number 12. The equation for the combustion of the ethanol is given. C2H5OH plus 3O2 is giving us 2CO2 plus 3H2O. Rewrite the equation and show all the bonds. So we have to just make an open structure here. So C2H5OH actually have two carbons having 5 hydrogens attached to them. These all will be the hydrogens attached to these two carbons. So it is C2H5. Then it is attached with O, and O is further attached with hydrogen. So remember here all the single bonds will come, not the double bond. O can maximum make 2 bonds. So with this carbon, O is attached, O is attached. This O is further attached with hydrogen like this. So this is the structure of C2H5OH. Then we have 3 total O2. O2 makes the double bond. So oxygen and oxygen have the double bond 1, then second O2, then third O2. So 3 O2 total we have here. And it is going to make 2 CO2. In carbon dioxide, carbon can make maximum 4 bonds and oxygen can make 2 bonds. So one carbon is going to make bonds with 2 oxygens double so that total bonds can be complete. And we have 2 CO2. So like this we will be having 2 CO2. Plus we have 3H2O here. Water has a band structure, one oxygen with 2 hydrogens. So one oxygen with 2 hydrogens like this. And we have total 3 water molecules. So all 3 water molecules you have to make here like this. So this will be a final open equation showing all the bonds for this combustion of ethanol. So here is the same equation that you can see. Part B, use the following bond energies given in kilojoule per mole and calculate a value for the standard enthalpy change of the reaction. So this reaction in the first line is given that this is the combustion of ethanol. So in this reaction, actually, we have two sides of the equation. We have this reactant side, we have this product side. And if you remember, reactants always have breaking the bond. In reactant side, we always have bond breaking. And bond breaking is always endothermic reaction. It means the positive values we are going to use. And product side always have the new bonds formation. And in the product side, we will be having exothermic reaction because bond forming release energy. So it will be negative energy. So we have to just identify how many bonds we have on the reactant side and how many bonds we have on product side. So first of all, in case of the ethanol here, see, we have one CC bond, like this you can write, and we have CH1, CH2, CH3, CH4, and CH5, 5 CH bonds. And then we have one CO bond single, and then we have one OH single bond as well. And then we have O and O double bond, 3 total. So this is all about the reactant side. In the product side, we have CO bonds 1, 2, 3, 4, and all are double. So 4 C double bonds O we have here. And in the water, we have OH1, 2, 3, 4, 5, and 6. 6 OH bonds total. So now what you have to do, you have to just add their values together. But remember, for the bonds breaking value, all these values you will be using the positive from here. And for the bonds formation, you will use these values with negative sign because they are exothermic values and they will be negative. So what will be our formula for delta H combustion? It will be equal to enthalpy change for bond formation, bond breaking plus enthalpy change for bond formation. So you can use two different colors so that there will be no chance of mistake here. So for the bonds breaking, we have all these bonds that are breaking in the reactant side, and we have all these bonds that are going to form in the product side. So these all values we are going to write positive plus of the formula, and this value we are going to use negative 4 times negative value of C double bond O and 6 times negative value of OH single bond, and then just add these together. You are getting minus 6010, and this will give you the answer 4686, and final answer you will be getting minus 1324 kilojoule per mole. So final answer you are getting negative. It should be negative because this is combustion. And we said that combustion reactions are exothermic, giving us negative answer at the end. Part C, the actual value of the combustion of ethanol, if we have by experiment, is minus 1367.3. But the answer we are getting is minus 1324 here. So we are getting a little different answer as compared to the experimental value. Our calculated answer is different as compared to experimental value. So we have to tell the reason why this is different. Remember one thing here, these bond energy values that we are actually using, these are not the exact bond energy values. These are the average bond energy values. What is the difference between the exact or the average? Let's take an example here so that you can understand what are the exact bond energies and what are the average bond energies. We have, let's say, ethanol C2H5 with OH here, and we have, let's say, a water molecule. And we are going to see the bond energies of the OH. We have one OH bond here, we have one OH bond here. So if you see, it looks the same OH bond in both. It is looking like that the OH is same in both. But in real, this OH is not the same because environment is not same here. Environment means which things are attached here. So if you see here, in the water, just hydrogen is attached with this OH bond. So each this OH bond should have a little different energy needed to break this bond. But in case of the ethanol, you see the OH bond is attached with a big group C2H5. So it means a different value is needed to break this bond because its environment is different. Its attached group is different, which will affect this value. But what we do, we most of the time just use the same value. Same 465 we use for this one, same 465 we use for this OH bond. Why? Because these are not the exact bond energies, these are the average bond energies of all types of the OH bonds. We can have OH in different situations, so we cannot remember the exact value of the OH bond in all cases. So we just take the average value. So that is the reason when we do the calculation by using the average value, we get a little different answer as compared to experimental value. If we use the exact value, if we use the exact value, it will be different for this OH, it will be little different for this OH, it will not be same 465, it will different, it will be different in both cases. So if we use the exact values, then we can get the same answer 1367.3. But right now we are using just the average value of these all types of the OH bonds so that we can just use the same OH in both cases. So that is the reason we are not getting the exact answer just like the experimental value. So same reason you can just write here that bond energies used in the calculation are actually the average bond energies. They are not the exact bond energies. So from the data, we are just using the average bond energy. It means it is not going to give us the same value just like the experimental combustion. It is going to give us a little different answer. Question number 13. Look at this equation and see which of the following statement is completely correct here. So, here they are talking about the bond breaking and bond forming. So, before moving toward the options, just see from the equation, the reactant side will be the bond breaking side. It means it should be endothermic. The product side is the bond formation side. It means it should be the exothermic side. So, like this, you can just minimize some of the, you can just cancel some of the options here. So, we have the endothermic as the reactant and we have the exothermic as the product. It means only the option B, C, D can be correct because it has the endothermic here and it has the exothermic as the product side. Okay, now see how many bonds are going to break and how many bonds are going to form. So A option is not correct because it is giving us the bonds breaking at exo. So A we can just cancel. Now, CH4 has 4 CH bonds. So, in all options, we have the 4 CH bonds. Okay. 2O2 have the 2 oxygen bonds. So, 2 oxygen bonds we have here, but O2 don't have the single bond. So, we can just cancel the C over here. And O2 have the double bond. Okay. So, now B and D can be the possible answers. In the carbon dioxide, two C double bond O are going to form. So we have two C double bond O bonds here and we have two C double bond O bonds here. So far both options are right. Then in case of the water, one water have two OH bonds and two water will have four OH bonds. So four OH bonds we have, not the two. So B option will be the right option here. So 4 CH bonds and 2 OO bonds are broken in endothermic reaction. 2 C double bond O bonds and 4 OH single bonds are formed by exothermic reaction. So B option will be correct here. That's all about the self-assessment question of chapter 6, Enthalpy Changes.